Good morning, everybody. My name is Dan Lipsa. I'm from Kitware. I'm a research and development engineer there. So I'm going to talk to you about ParaView. First, I'm going to have a few slides on Kitware. I'm going to have an introduction to ParaView, basic usage, and then talk a little bit about visualizing large models. So at Kitware, we have 5 groups. We collaborate within the groups, but each group has sort of its own specialty. So we have a group in computer vision, data and analysis, high-performance computing and visualization, medical computing, and software process. The computer vision group looks at identifying features in images and videos, and also processing social media and discovering features there. Kitware is an open source project that this group produces and maintains. Data and analysis, they do mostly more traditional information visualization. They do most of their work on the web and also data management. They do a lot of visualizations on maps as well. Resonant is their open source project they produce and maintain and work with. I'm part of the HPC and Visualization group. We do traditional scientific visualization there. We maintain VTK, the visualization toolkit. This is a visualization library, C++ library, with hooks to a script in Python, Java, TCL. ParaView, this is the application for visualization. And also these two are two ParaView-based applications. TomVis is focused on material sciences. CMB is a modeling tool, so it allows you to build models and visualize them. The medical computing group, they produce ITK, the segmentation and registration toolkit, 3D slicer, and Pulse. It's a newer product. It's a physiology, whole body simulation. And the software process, we produce CMake and maintain. So all these projects, you know, not only Kitware works on them, but we collaborate with many research groups and commercial companies. So they're all open source projects, so anybody can contribute to these projects, and we want people to get involved in those. So CMake is a C++ configuration and build tool. So if you build C++ programs, it's one of the most popular tools for building C++ programs. Okay, so I guess in this presentation, I'm going to show you a number of examples that hopefully will get you comfortable using ParaView. So if you didn't already, please install ParaView 5.5.2. That's the latest version. If you have an older version, that's fine as well. Probably it's going to work as well. Maybe the last step, you know, when we try to connect to Cooley, maybe that's might be a little more problematic. But yeah, most of it should work just fine. So ParaView is an open source, scalable, multi-platform visualization application. It supports distributed computing. It has an intuitive user interface. It's extensible and modular. It's an open source using the BSD3 clause license. So that means even commercial, so it's open source. The source code is freely available, but you know, the difference between BSD and GPL is like even commercial companies can take the source code and sort of build their own commercial products with them without worrying about licensing issues. So that's important because we have a lot of commercial companies that collaborate with us, and they don't want to worry about licensing issues. We offer, at Kitware, we offer commercial maintenance and support. So one of the points here is that it has a modular architecture. So ParaView is actually many tools. You can use ParaView on the desktop the way you are going to do it. This has a Qt interface, so you just load it as a standalone application. You can use ParaView on the web. So this has the same server side tools, but it has a different interface. You can do your, build your visualization pipeline and see images in a web browser. You can control ParaView using a Python script. So, instead of doing everything with the interface, you do it through a Python script. So that's important if you want to process many images and do the same processing on those. You can have a script and don't need to use the interface anymore. In ParaView, we can generate images to visualize in these cave environments or immersive environments. And also, ParaView was built for running in parallel, so it runs well on these high-performance computers. And ParaView Catalyst was mentioned in the previous presentation. So this is a library, a subset of ParaView that you link with your simulation and allows you to analyze and visualize the data for every time step of the simulation. So the simulation runs the time step, passes its data to ParaView, you run the visualization, you produce an image, and save it on disk. I mentioned before we have many custom applications based on ParaView. So ParaView is developed in such a way that makes it easier to develop these custom applications. So the idea here is ParaView is a general purpose visualization application. Because of that, it's very detailed, but it may be difficult to use for non-experts. So with these custom applications, we work at a higher level of detail. We build the visualization specifically for a domain. And we know the pipelines, we know the processing that they need, and we make the interface easier to use for that particular domain. And this VeloView is a custom ParaView application designed for LiDAR data. So ParaView is used in many places by academic, government, and commercial institutions. It's downloaded 135K times per year. It got a number of awards. Data ranges, so you can use ParaView for data stored on your desktop, up to billions of cells on these large high-performance computers, parallel computers. Yeah. So the architecture of ParaView, at the bottom level, we render images using OpenGL. We do communications using MPI. IST is a rendering tool, parallel rendering tool that allows us to render the pieces produced individually by each nodes. We compose those images together using the IST library. VTK, that's the visualization library that's used at base of ParaView. ParaView server, it's, I guess, the engine behind ParaView. It does all the processing and the visualization. And then we have the interface that can be Qt. We can have a Python script that talks to the ParaView server. We can produce the interface on the web, or we can have a catalyst. I guess your processing and visualization pipeline is linked together with your simulation, and the pipeline is expressed as a Python script, but all the data is transferred each step from the simulation. And also we can have custom applications where the interface is customly built to sort of make it easier, work at a higher level of abstractions for specific domains. ParaView development is started in 2000. The first release was in 2002, and these are some major changes that went into ParaView. For ParaView 3.0, the GUI was rewritten using Qt, That's in 2007. Before that, it was TCL-TK. ParaView 4, we redesigned the property panels. So these are basically all the properties that you set for your processing steps, for your filters. And ParaView 5.0, we rewrote the rendering backend to use modern OpenGL. Before that, we used sort of legacy OpenGL with a fixed pipeline. Now we are using shaders and all the modern OpenGL features. So current funding, we work a lot with many national labs and also with commercial companies and other contributors such as universities. So visualization, you convert your data into images on the screen, good-looking images, and hopefully those will help you better understand your data as well. Data types, these are the basic data types used in ParaView. So all these data types represent points where you store your values, the values that you measure, and also cells used to interpolate those values so that you get your measurements at different locations than the points. Yeah? And these types of data enable you to do more optimization. So if your data is regular, you can occupy less memory, your algorithms run faster, and as it becomes less regular, you have more flexibility to store your data, but your algorithms probably are going to run slower, and you're going to occupy more memory. So ParaView has an extensive help system. So if you have, let's see if I can switch here. Okay. Oh, you don't see that. So I have to get out of the, I'll do that. So we have a ParaView guide. I'm going to end the slideshow and just use regular. Okay. So now I can switch. Yep. So ParaView guide. This is a comprehensive reference for ParaView, and this is available in the help menu. Help. ParaView guide. Yeah, you can, and that will take you to the website and download that on your machine. Tutorials. There are several tutorials available. These slides are actually based on the ParaView tutorial. This is a PDF document that sort of goes into more details, and it's a document, and it takes you through many examples to learn how to use ParaView. So these slides are based on that. ParaView website. That's a good resource to see everything that's available. Also, we have a discussion forum, discourse@paraview.org. We recently switched to this forum. Before that, we used mailing lists. Yep, so this is the help menu. You can look at it as well. We have a getting started, and it shows you a few things. I think it's just a page with a few things. The reader, filter, and writer reference, that's it's a good thing to see exactly what is available, what sources, what readers are available in the compiled binary. ParaView can be compiled in different ways, and if a certain reader is not available in the binary you have, you can compile it yourself and possibly enable that reader. So you have to look at that and the writers that are available. Yeah, it's a long list. Okay. So basic usage. I'm gonna start the presentation again. Okay. So like many other applications, we have a menu bar. We have toolbars to store the most commonly used operations. This part here, that's the pipeline browser. So This shows you every processing operation that you're gonna do on your data. The properties panels, this show you properties you can change for the selected filter or processing in the pipeline browser, and that will change the processing. Will adjust how the processing is done. So if you get lost, well, it's very easy. You have many panels, and these are very configurable. I'm going to close this. It's very easy to click on an X here, and that disappears. What do you do then? You can go to View, and all the panels are listed in here. Have to know this was called the pipeline browser, yeah? So you can bring it back, yep. And everything else, all the toolbars are listed in this View menu, yeah? So we're going to go through a number of examples. We're going to start with very simple ones and build upon that. Yep, everybody has ParaView installed on his laptop. Yep. Okay, so you can also sort of follow along. So let's create a cylinder. It's called a source because it produces an output, but it doesn't have any input. Regular processings are called filters. They have an input and an output. Writers are the ones that have an input. They don't have a data output. They just write their output to disk. Yeah. So I'm going to reset here. So I was doing something here. Okay, so we have to create a cylinder. Yeah. So you go to source. These are alphabetically. So cylinder. And then you have to click apply. Yeah, so this is how ParaView works. You always have to hit apply. And that's your cylinder. You can look at it, yeah? You can play with the camera manipulation controls. Yeah? So this button here, reset. It resets the object so that you see it nicely on the screen. You can orient your object, your visualization, and well, this is harder. Okay. This -z plus z, so minus means it's pointing toward you. Plus means it's pointing toward the screen. Yeah. So Y is up. Y is sort of pointing toward the screen. Yeah. Y is pointing. So plus Y. Yeah. Plus pointing toward the screen. Minus I pointing toward us. Yeah. Okay. You can rotate your object. That's not here, this is here. Yeah. So rotate. And also, this shows you the orientation axis. This allows you to, so this button here allows you to pick the center of rotation. So this is important. If you have a model with several objects, you want to rotate around certain object, you have to click on that. I don't have that here, but I can click here, and now your scene is going to rotate around that point. You can reset the center of rotation. Oh. This way. Yep, and now it's back. Yeah? So this is the button to reset, I think. Yep, reset center, and that shows center. You show an axis in the center of the object. You don't see that now because the object is not transparent, but we're going to see later how you make it transparent. Okay? All right, so let's change some properties. So you have the same cylinder. Let's increase the resolution. So you see your cylinder has 6 sides. So you go to properties and increase the resolution here, make it 60 sides, yeah? So that's going to be a lot rounder. Yeah? Notice, I don't even sort of pay attention to that, but every time you change something, you have to click apply, yeah? So why is this apply button? ParaView is designed to work with large data, and if auto apply would be on, you make a change and then sort of ParaView hangs and process that large data. If you have this separate step where you say apply, you know that a large processing is going to come, and you are prepared for that. Reset, notice how that works. So you change something, reset sort of brings it back to the previous value. Yeah, so it doesn't apply the change, it just sort of undoes the change. Yeah, and delete will delete the filter from your processing pipeline. You can copy and paste all the parameters in a filter to other filters in your pipeline. So that is common many times in your processing pipeline. You have several filters of the same kind, and you've done the parameters in a certain way. You want to copy all of them to different filters. You can do that with the copy paste. The save button here allows you to save defaults for your filter. So for instance, instead of 6, you want your cylinder to have more edges. Yep, so cylinder, notice it has 6. Yeah. So hey, you say I want to have more of them, 65, and you click save here, and then delete, and then do source cylinder. Notice it has 65. So it has the values, the default values that you like better. Yeah. Reset brings it back to the application default settings. You have to save again. Yep. So save again, and then do that source cylinder, and that now has 6. Yeah. Okay. So these are, notice we have 3 areas in our properties panel. We have properties for the current filter. We have display properties. So the display properties are associated with the data produced by the current filter and the selected view. So you can have different display properties for the same filter, but a different view. Yeah? And the view properties are associated with the view. So the kind of display properties are you can change the color, you can rescale the color mapping, you can change the opacity. So let's try to do that. Let's select a new color for our cylinder. So let's see, in the display properties, you can edit here the color map. There is no scaler, so that means you just change the color. So let's make our cylinder red. Yeah. Notice the same button. It's also duplicated in the toolbar. Yeah, so this does the same thing. Change the kind of red I have. Well, this is more like an orange. Okay. Render view options changes the properties for the view. So some of those are the background color and the orientation axis visibility. So let's see. Let's try to look at that. So that's axis grid, actually. That's a good property to look at. This puts you a grid around your scene, and you can see how big your data is, yeah? along X, Y, and Z axis. So this is what we've done here. We turned on the axis grid. Okay, as you can see, you have many properties here. Our properties are split into regular properties and advanced properties. So regular properties are, I guess, the most commonly used. Notice, well, this pattern here shows you advanced properties. So you will see many more properties if you select this. Also, you can search for properties with the search bar. So you can search for, let's see, we have this specular. So let's try to search for specular lighting. So we can change the specular lighting. Notice that property was brought in. We changed it. You see some specular highlight here. You have to move your cylinder around. Otherwise, you might not see it depending on how the light falls on that cylinder. And you can increase that. Notice you don't need to hit apply if you change the display properties or the view properties. This is because OpenGL is quick, so anything that you change visually, OpenGL can render it directly. Yeah? Okay, so we changed the specular and played with that. You can look at opacity. So the trick with the search button, it's often that you forget those couple of letters you typed in there, and then you look for a property and you cannot find it. That's because only the properties that match those few letters are displayed. So you have to erase that, and then opacity. Yep, so you have the opacity here. And make your cylinder slightly transparent. You see the center marking axis as well. Yeah? All right. So the auto apply, you know, if you prefer, you can set that on. You won't have to go through the extra step of clicking apply. I never do that, so I won't go over that, but you can play with that if you prefer. The color palette allows you to change the background color, but not only that, all the associated colors, for instance, the grid color, so that your visualization looks good. This is the color palette. It's a palette. Oh, wow, I don't know why. So the default background is this gray one. You can have white background if you want to print your image. And notice the axes were changed to be black. So the idea here is you have a set of colors that are all changed in the same time so that your image still looks good. So I will advise you to only use that if you want to change colors. You can also change individual colors. Here we show all the colors that are changed when you change the palette, yeah? And you can play with that if you want to.
Question.
Yeah?
Under the color palette, what's the difference between the print background and the white background?
It's a good question. I don't know the answer to that.
They look the same to me.
Yeah. It might be, some of the colors might be different if you look for a list of all colors, but I don't know the answer to that. Okay, so we have undo and redo. So we have two kinds of undo, redo. So the undo basically reverts the last change you made. So that refers to properties. So notice one change was I changed the palette, and then I made the cylinder transparent, so that was reverted as well, yeah, transparent palette. So all that works fairly nicely, so that may be useful if you made a change and you don't really know what you changed and things don't look good anymore, Yeah. We also have undo redo for the camera position. You rotate your model in a certain way. So these are here on the view. So notice these are the various changes I made. Yeah. Okay, so delete cylinder. So that's the last thing we're going to do. We played enough with the cylinder. Deleted. The axis still stays. Notice I don't have any properties here. That can be confusing. What happened? Oh, these letters are here. So it happened to me. You leave something there, and then you look for a property, and it's not there. Yep, so you can remove the axis grid. You can remove the center axis. Okay. Supported data types. We support many data types. It's a long list here. As I said, if the binary that you downloaded doesn't have a certain reader, it's possible that that reader is supported when you recompile ParaView. That is because many times readers make use of an external library, so you have to have that installed on your machine and link with that, and you can add your favorite reader that way. If that's not available, you can create a reader using Python. So this is the programmable source, allows you to write a Python code that reads your data and creates the VTK data types that we expect. Another possibility is to create that reader in C++. This has the advantage of allowing you to create interface as well. So those properties that you can set in there are specified using an XML description. Yeah, so you can do that. It's sort of more advanced. You have to have the right CMake to build that plugin. So you'll have to do more work. Recently, that's not available in the latest release, but it's available in the GitHub, GitLab code. We added the ability to create both the reader and the interface using just a Python file with some Python markups. So this link shows you some examples of that. So you can write your reader, which is a full ParaView plugin. That is, it can be used as anything else available in ParaView. You can write that only in Python. You don't need to compile anything. Yeah. So, okay, let's look over some other examples, more advanced examples. So let's load this disk file. We load that from where ParaView was installed. So let's switch to ParaView, open. I already have that in here. So in my case, I'm on a Mac, Applications, ParaView 552, Contents, Data. That's where stuff is. We have 3 small data examples that can be used for presentations. So let's load this disk file. Before this file is loaded, notice we can set that we want to load only certain variables. In our case, we want to load them all. This is useful to save memory if you have very large data sets. Yeah? It's not the case here, so we load everything. It's just a disk with a hole in it. It's a cylinder with a hole in it. And it has several data values here. For instance, you can color by pressure. Okay. So let's look over the toolbar that allows you to change how your data is displayed on disk, on the screen. So this toggles the color map here, the color legend. This allows you to edit the color map. We'll go over that. We use this to color an object, but in our case, things are more complicated because we have a mapping between scalars and a color palette. So rescale, scalar range. In this case, the colors you see on the screen, we map a range of scalars to a color palette. Yeah. So rescale, that scales to the full scalar range. You can rescale to a custom range. That's useful when you have a data value that's an outlier that will sort of change your mapping in that, for instance, everything will be blue here. So in that case, you can use a custom data range. You can use a data range that goes over all the time steps and looks at the ranges for all time steps, and it gets the encompassing range for all the time steps. Or you can scale to the scalars that are visible. This allows you to change the scalar or the vector you color with. Yeah, you can color with the pressure, or you can color with the temperature. In this case, the temperature is red in the middle here. Or you can change how the data will be represented. You can show surface with edges. Yeah. We can show a wireframe. Yeah. So as I mentioned before, you process your data by building a processing pipeline. In this pipeline, you have a list of filters. These are common filters that we use. So we can use the calculator filter to create derived data. For instance, if you have an attribute A and an attribute B, it's easy to calculate A plus B, or A, any mathematical operation plus B. Sorry? Like that? Yeah. So contour does, yeah? It's where you install ParaView. It's a good question. I think it's a cylinder that maybe it was sort of extruded in a certain way, and it shows, probably it is a simulation, and it shows what happens with the pressure and temperature. But yeah, I don't know more besides that. So the contour filter creates an ISO surface. That is, it creates these surfaces that go over all the scalars with the same value. You can clip your data, you can slice your data, you can apply a threshold, that is, select only the data that has values within certain ranges. You can extract a subset of your data. You can apply glyphs to your data, that is, apply glyphs in the specified points in your data, and data is sampled there, and your glyphs are going to be, the visual properties of your glyphs are going to be determined by the data sampled at those locations. You can do streamlines using stream tracer, warp the data based on a vector or scalars. You can group data sets so that you can apply processings together, or you can extract a data set. We'll cover most of these in the next examples. So filters are organized in ParaView in sort of groups. Also, you have a group that contains all of them, where filters are stored alphabetically. There are about 150 filters, so quite a few filters to learn. The common ones that we're going to cover will take you a long way to visualize your data. So selecting the filters with the mouse may be awkward if you have to go through 150 filters. So we have this search facility, the quick launch, where you just type a few letters from a filter, and all the filters that match those letters are going to be displayed. So for instance, the extract surface, you can type, I guess, a group of letters, the surface, and then extract. That's going to select the filter that you want. Yep. So control space will bring up this quick launch in Windows and Linux. Alt space will do it for Mac. Okay. So you can play with that. So you can play with that. Yeah, alt space shows you that, and then contour will bring you the filter. Enter. Yeah. Okay. So let's apply this contour filter to the disk, and we're going to contour on the temperature and change the temperature to 400. Yeah. So let's try to do that. So we bring up the quick launch. We write contour, contour. Yeah. Apply that. You have to specify what is the scalar you're gonna take an ISO surface for. So that's temperature. And then change this to 400. And then apply. Yeah. So this notice is colored by pressure. If we color by temperature, well, temperature is not here, but it has the same value, the same temperature value. Yeah. So let's create a cutaway surface. So this is a volume. Yeah. We want to create a cutaway, just the skin of this volume. So we do that by selecting what we want to take the skin of, yeah, which is our disk, and then extract surface, type surface, extract surface, yeah. Enter, and then apply. Notice we have a surface that covers everything. We can, this eye here will show and hide the surface. So this is different than the actual data. It's just the skin of it, yeah? So let's, after we have the skin, we can cut this with clip. Yep, so just cut through this skin. We leave it, you know, we could change the plane we cut with, but just leave the default one. Notice right now we see the skin and we see our original surface. We can remove these widgets by removing this, unclicking this show plane. Yeah? So note, remember you can orient this with these buttons here. Plus, minus X is the right one. Okay? Yep.
So what is the funny mushroom shape?
I'm sorry?
What is the shape, the
that is an iso surface, that is a surface that goes through the scalar, through temperature. So all those values on the surface, they have 400 degrees. That's right, that's right. All right. So if you look in the pipeline browser, this shows you the pipeline we have for processing this data. So we show this tree in this case. It can be a graph in a strange way to sort of save space. So that's the tree that you would regularly, that's how you would regularly show the tree. You have a contour, and then extract surface, and then the clip. We sort of show the same thing, but in a more compact way. So you have the disk, and then that has two children, contour and extract surface, and then the clip. Clip is applied to extract surface. Yeah? I already used these. So you have these eyes on the side of the pipeline. If the eyes are showed with regular colors, that means the data produced by that filter is visible. If they are grayed, that means the data is not visible. Yeah. So you can play with that. Well, actually, the eyes. This is an old image. Before the eyes were grayed, now the eyes are closed. If you pay attention to the eyelids there, so if the eyes are closed, that means you cannot see the image. Yeah. Okay. So if you wanna start over, reset ParaView to how it is when you just started, you can click this button, reset session. Yeah. So let's do that. Multi-views, so you can have several views displayed in the same time. So let's do that. We're gonna load this disk file, and then color by pressure, and then color by temperature. Yeah. So let's do that. So we loaded this file, recent files, disk. Yeah. Don't forget to load all the variables. So we load the disk. We can color by temperature. Yeah. The way you create a new view is you can split the current view either vertically or horizontally. So let's split it horizontally. Create another render view. And now you can show the data you want in this empty view. Yeah? So in our case, we show the disk here. And color by pressure. Yeah? So this is kind of not very satisfying because these data objects are oriented different ways. So you can synchronize the views so that they're always oriented the same way. Right-click, link camera, and then click on the other view. Yeah. So this way, so right-click on a view, link camera, and then click on the other view. So this way they are sort of synchronized. Yep, and you can compare two data sets, I guess, two different scalar values to see how they look like together. Okay. You can move, sort of switch views around by dragging on the text and dropping it to where you want it to show. Yeah. So drag on this. Yeah. And also you can adjust the width of each view. Okay. All right. So let's reset. So let's look at streamlines. So we're going to look at the same data file, yeah, and apply this stream tracer. So we're going to load the file, recent files, disk, load all the variables, apply, yeah. So now we click on this stream tracer, or you can bring with the quick launch, yeah. So stream tracer. So remember how streamlines work. You have another data set, such as a line, that is going to allow you to seed the streamline. So that is, they're going to start from the points of this line. In our case, we just want our seeds to start from a point. So let's see. Okay. So the seed type, high resolution line source. I'm going to use that a point source. It's not actually a point. It's going to be a sphere with many points inside that sphere, yeah? So seed type and apply. So now we don't show the disk, but we show the streamlines generated from that disk. And we seeded those streamlines with points, random points inside the sphere. We see the sphere, still see the sphere, so we can click to hide that. So notice these are lines. When you have just a line, you cannot apply lighting to it, so it doesn't look that good. So what you need to do is to apply a tube filter. So that's going to put a tube sort of around this line. So just apply the tube filter. Right now, your streamlines are going to look a lot better. Yeah? Let's add some glyphs. So streamlines show you nicely how your vectors flow, but they don't show you the direction where your flow goes. So let's apply a glyph filter. That's the tricky part here. You apply the glyph filter to the stream tracer. Yep. So you want to apply the glyphs along the lines generated by the stream lines algorithms. Yep. So you can click on this glyph, or you can search for glyph. Yeah. So again, we apply that to the stream lines, not to the tubes. Yeah. So when you apply the glyphs, you want to specify what's the property that you want to use to change the glyph properties. And in our case, that property is going to be V. Yep. You want to scale the glyphs by the vector. And also, you want to change the scale factor. So notice here is 0.7. If you click on that, it's going to be 0.05. So it looks at the range of values of the vector, the V that you chose, and it scales those glyphs appropriately. And then you can click apply. Can increase this a little bit if you need to. Yeah. So we can color by temperature. Oh, I think a step there was to choose the glyphs instead of arrows, to choose the cones. And now I don't need to increase anything. Yep. Could you follow along? Any questions? Yeah? Okay. So when you build one of these pipelines, it's always you have to think. So that's a common mistake. You apply the processing to the wrong data. In our case, we had to apply the glyphs to the stream tracer, not to the tube or to the disk. Yep. So we want to place the glyphs along those lines that were created by the stream tracer. Okay, so we have some questions here. Where is the air moving the fastest, near the disk or away from it? Near the disk or away from it. So it's near the disk, yeah? At the center or near its edges? Edges, yeah. Which way the plate is spinning? Well, I think that depends on if you look, but if you look from this side, it's going to be, what, clockwise, yeah? So at the surface of the disk, is the air moving toward the center or away from it? So surface of the disk, moving toward the center or away from it? You see that? Well, I think it's moving toward the center, but isn't it? So it kind of moves toward the center if you look at how the spirals sort of unwind. So you have the left button, the right button, and the middle button. So if you don't have two buttons, you have to choose Control and Shift. So for me, the left rotates, right changes the zoom, or the zoom wheel changes, yeah, and Control and Shift, and the left button pans. So left rotates, right zooms, and Control Shift and left pans. So okay. Okay, so reset, and let's look over some other examples. So we're going to look over some common data analysis filters. So first, we're going to look over plot over line. So this sort of shoots a line through your data, and it samples the data along that line, and then it builds a 1D plot showing you the values that were sampled along the line. Yep, so we can do that for the disk file. Yep. So let's try to do that. So we load the disk, load all variables, apply, and then do this plot over line. Yep, this one. Or you can use the quick launch. Yeah, you can see plot over line. Yeah. So notice it shows you a line. You can use the mouse to drag this line around to specify how you're going to position it. You can use also, this is the cut disk. So let's do that the same, yeah? So I'm going to delete the plot over line and then cut the disk. So use the clip filter. Yeah. Apply. And show plane. And the disk is colored by, I think that's temperature, yeah? This is -x, okay. And then you can do plot over line. You want to sample the whole disk, not the clipped part. Plot over line. So you see the line. You can move the points around, but you can move them also in a more structured way. So 2. So you move your mouse around and press 2. That will position the second point, yeah? You can also, let's show here, when you show the clip, I'm going to show surface with edges, yeah? And then again, set plot over line. So 2 positions the point. Control 2, or Command 2, I think in my case, positions it at the actual points. You see? The same way 1 positions the first point. Command 1 or Control 1 positions it at grid points. Yeah? So, you know, after this great way of using the interface to position your points, you realize that actually the best way is to just specify the values by hand. And you do that by specifying the values by hand, 0, 0, and then 0, 0, and then 10. Yep. So this will sample your data along this line. So click Apply, and you'll get a 1D plot with the values sampled along the lines. What values? All the values in the first case. Yep. So we're gonna stop here and continue after a break. All right. So we're gonna continue with our plot over line example. Yep. So we position our line with the interface, but you know it's always difficult to position something in 3D with precision with a mouse, the regular mouse. I never tried a 3D mouse, but probably not that easy either. So the best way is to specify those values by hand. So we're gonna plot values between 0 and 10 along this line. And notice we plot all the scalars and the vector magnitude as well. They have different ranges. So this is just the value. Yep. And if you have large values, many of the plots are all sort of crowded here at the base. So we want to show just temperature and pressure. So let's do that. We're going to look at the display properties. Notice all values are listed here. So we unselect most of them, leave pressure and temperature. Notice the legend here shows you that. Let's see, we have some. Okay. Yep, pressure and temperature. So I think this is temperature. Yep, this is temperature. Pressure is very small. Yep. So, but you want to see how these two values sort of compare. You know, when is one growing, what happens to the other one? So how can you do that? You can say that I want to show the values for pressure on this right-hand side axis. So you select pressure, and then you say that the chart axis should be bottom right. Yep. So right now, you see the values for pressure, which are sort of around 0, from 0.01 to 0.028. And these are the values for temperature. Yep. Yep. So this is allows you to sort of compare you know, the growth of wildly different scalar values. Yeah? You can also, I didn't show you that, so you can sort of move around this, so you can pan the plot. You can also zoom in, zoom out. This reset view shows you the plot from the original view. It sort of places it nicely in the graph. You can move the views as you've done before, yeah. So we already done that. We showed the pressure on the right-hand side axis. You can add a histogram as well for temperature. So let's do that. Again, it's important to realize what data you're going to process. Yep. So you don't apply the histogram on the plot because nothing is going to come out of this. You have to apply the histogram on the disk. So you select the disk, and then you bring up the quick view and type histogram. So let's see what I do here. So select the disk, histogram, enter, and then apply. So you have to specify what what variable you're gonna do the histogram on, and that's temperature. Yeah. And press enter. Yeah. Okay. So we got this nice looking plot. Okay, let's reset. And we're going to look over how you do volume rendering. So the same data set, you want to do volume rendering for temperature. So file, you load the disk, load all the variables, apply, yeah. And then change the representation here to be volume. Well, let's color it first by temperature. So temperature is here in the middle, red. And then do volume. You might see a dialog there saying that it might be slow. Press yes and never ask again, and you'll see the volume rendering for this. You can adjust the color map, the color mapping for volume rendering, and you do that by clicking on this button here, Edit Color Map. Yeah. So the bottom part here changes the colors. The top part changes the opacity. Yep. So how do you change the color? You add these control points, which you can drag on. So you can drag on that. So yeah. So this changes the colors. If you don't like something, a control point, you can press delete when you select it, and that deletes it. Yeah. So this brings you to this original range of colors. Yeah. You can drag this line. It's the same idea. You add control points, and then sort of adjust your opacity to see only certain features. Yeah. So you know that the range of values you are interested in, this works well with medical visualization. Bone is within certain scalars. You show only that, and you'll see just the skeleton, or you see just the skin, from an X-ray. Kind of the same idea is here, happens here. Yep. And pressing delete will delete these control points. Yeah. So you can play more with this and sort of go over what we've done before. You have this nice volume visualization. Let's add streamlines. Yeah. So stream tracer. We add that. We change the seeding to be a point. Apply. We can hide the sphere. Yeah. So you have these lines. You can make them tubes. Yeah. And you can apply the glyph as well. You have to be careful not apply the glyph to the tube, but apply it to the lines. So glyph, choose cone, and you glyph V. You scale by vector, and you rescale to the current range, yeah, and apply. So you have this nice looking visualization where you have volume rendering, glyphs, and also streamlines. Yeah. Okay, so we looked over the transfer function. You can change also the color palette, so the default one is this blue to red. You can choose black body radiation. It's another nice one. You apply. Oh, so I changed that only for the glyph. You have to change that for this as well. Apply. Yeah. Yeah. Can leave the color, the tubes white. Okay. Okay. Okay, reset, and let's look at the data with time. So everything that we've done so far was static. ParaView can process time-dependent data as well, so reset session. And we're going to load a different data set from the same location. We're going to load the CAN data set. Yeah. So the same location, can.ex2. Load all the variables, apply. So this is a can, that, half a can that's squashed by a brick. Yeah, so think plus y is a nice view. And notice you have these play VCR controls, if you know what the VCR is. Yep. Nowadays you don't use DVD play controls, I guess. Yeah. Okay.
How do you generate those files?
These data sets are generated by various simulations. So, our collaborators, I have to learn the history of those. Probably very few people know that because, I've been with Kitware for 5 years and I always used these data sets, so they were generated before that. So,
do you have to save the data in some kind of format?
Yeah, the EX2, I think it's Exodus format. So on this toolbar, you can go to the first time step, go to the last time step, yeah. Go forward one time step, backward one time step. You have the time step value, and then you have the time value. So often, simulation generates these time values, and the difference between two time steps is always 1, but that's not the case for the time values. Yeah, so the simulation time may be very different than the actual time step. We have 43 time steps. Yeah. So let's look at common pitfall. Let's go to the first time step and color by EQPS. So color by, we are already at the beginning, color by EQPS, yeah? And then let's play. So notice these, the way the data is colored is very blocky. Yep, so that's kind of doesn't look right. So let's, the way to fix that is go to the last time step and then do reset, rescale to data range. Okay, and then go back at the beginning and play now. You see this looks a lot better. So what happened? The problem is the first time step, the range of data, all the values were 0 or around 0. And then when at subsequent time steps that range increased, you used the scalar range from the first time step. So your range was always around 0, but your data, your range at subsequent time steps was a lot larger. So that means you either had things blue, so if they were 0, or they were red. Everything was becoming red because your values were bigger than the initial maximum value. Yeah. So this is where this. So let's look at this. Information, EQPS. So notice the range here is 0 for the first time step, and then the range starts to grow. So the color mapping keeps the range that it's set for the first time step, and it keeps that. So the way to fix that, you either go to the last time step when probably you'll have better ranges, or you use a custom range here for your scalars. Yeah. Or you can use this rescale to data range over all time steps. So that means it's going to use the range of scalars that's the biggest for all time steps. Yeah. So it gets the minimum for all time steps and the maximum for all time steps, and it uses that range. Okay, but the problem with this rescale with the data range over all time steps is that it's going to go and read all the time steps in your data. That might be time consuming. The way ParaView works is it just keeps in memory one time step at a time. Yeah. So we've seen all these fixes. Okay, move to something else. ParaView allows you to query data based on time on scalar values. Yep. So you can query, let's say I want to see all the cells for which the scalar EQPS is greater or equal than 1.5. Yeah. So you do that. Let's go to the last time step. This is the button here. Find data matching various criteria. So you select EQPS greater or equal than 1.5, yeah? And you say run selection. You see a number of values are selected, and you see the actual values. And those are also shown on your data set, yeah? So greater than 1.5, and as you step through your data, fewer and fewer data cells are going to match that criteria. If you go to the first time step, nothing is going to match that. Yeah. You can also do so-called brush selection, so that is select elements using your mouse. So you can click on this. This is select cells on the surface. Yep. You draw a rectangle, and it's going to select those cells. After that, you can go back to this dialog and it shows you the cells that were selected. You can also specify that you want certain labels to be displayed for the selected cells. So you want to see EQPS. In this case, you don't see much because they're all crowded in there. So a better use for this is when you select, let's say, maximum. So EQPS is maximum. Run selection. For the first time step, everything is maximum because everything is 0. But then you'll see the maximum value, and also you'll see what that value is. Yeah. So maximum value keeps increasing. Yeah. Yeah. So go back. The clear selection. So what I've done is I went to this dialog and say EQPS is maximum. Yeah. Run selection. And also I said that I want to display this label for the selected cell. So display EQPS for the selected cell, close. And then as you go through the time steps, it shows you the maximum EQPS value. And it shows you where it is as well. Yeah. Okay. And you can clear selection this way. So if you look through these, let's see, buttons, you can have brush selection where you select either cells or points that are specified using a rectangle. You can select through, that is, you have a frustum that cuts through your data and selects all the cells that way, or points. You can select blocks, and also you can have this interactive selection. So let's see. This is good for inspecting, you can say, hover cells. So you can sort of move your mouse in the area of interest, and it shows you information about the selected cell. That is the cell your mouse is over. Yeah. So you have to unselect that. So hover cells on, and then unselect that. Yeah. So can play with all this stuff. Have various ways of selecting your data. Yeah, let's skip over that. We looked at labels. We added labels to your selection. Yeah. Okay, reset. All right, so this is the section where we played with the small data sets. Let's move on to visualizing large models. The good news is most everything is going to work very similar with what you've done when visualizing these small data sets. The connection is going to be different, but it's not that difficult. So to connect to one of these HPC machines, you have to have your login information. But besides that, things should be fairly straightforward. And also there are some, I guess, considerations you have to take in account when you visualize data, very large data. So Okay, so the way parallel visualization works is you split your data into these individual pieces and you run the visualization pipeline on different nodes and basically do your processing on those individual pieces. Most everything, well, a lot of things work fine just by doing that. So you do, for instance, you want to cut your data set. Yep, you just cut the individual pieces and then you put the results together. Well, you cut individual pieces, you generate the visualization for those pieces. And then after you generate the visualization for those pieces, you have to compose the resulting images, and you have to compose them in sort of Z order, so that because when you distribute your data on different nodes, you don't know that you visualize data from sort of behind that gets covered by a piece from a different node. So you have to compose your images in Z order, and you get the resulting visualization. Yeah. So, you know, this gets into more details on how ParaView is structured. So ParaView, the program that you've been using so far, has in it both, I guess, all three of these components: the data server, the render server, and the client. So when you run in standalone mode, you have all of them in the same program. When you run on these parallel machines, the data server and render server is running on the parallel machine. The client runs on your laptop. Yeah. You have these pipelines that are executed on each of the nodes on the ParaView on the parallel machine. Those generate a piece of the image. Those images are composed in Z order, and the resulting image is sent back to the client, or it's sent to one of these large tile displays. So I mentioned this before. When you run your ParaView executable, you have the client, the data server, and the render server in the same program. You run that by just typing ParaView or sort of starting the application from the user interface. You can also run PV Python that allows you to run a Python ParaView script. Yeah. When you run in parallel, you have to start your combined data server and render server. Start that on your parallel machine. You do that using MPI exec. You specify the number of nodes, and then the executable is PV server. So that's how you would run things on an MPI machine. You can do that on your local machine as well, just for testing. And then you run ParaView and then connect to this server. Yeah? So ParaView, in this case, is just the client. You can also run stuff only on the server with this PV batch, where you run everything on the server and produce an image that way. These are more advanced usages. This is what you would normally do to run stuff on a parallel machine. You know, this kind of is kind of complicated because you have to know how to submit the jobs. You already learned that with queues and stuff like that, so it's all complicated and might differ from one machine to another. Luckily, ParaView has a way to abstract this. You know, you can basically run the server from the client. So we have a number of configurations that are generated for many different parallel machines, HPC machines. So we have some for Argonne, Cooley, and Theta are here. So the way this works is let's reset this. You do File, Connect. I already have these configurations loaded. If you don't have them loaded, you do Fetch Servers. And here you have a number of configurations. And you can select the one you want and do Import Selected. Yep. So you do File, Connect. Yep. Yeah, so that's the, the good news is everything is, very easy to use if it works. Unfortunately, we have a bug in the current version of ParaView. We have a workaround for this. So you can download.
So it looked like you just did it, though. So how did it work for you?
I used the workaround. So basically, I used that file. That's right.
Okay, so but for me, it was crashing whenever I said fetch. So it wouldn't even let me go to fetch.
Oh, really? Okay. For 552?
Right, on Mac, yeah. So
okay.
The instructions that Marta sent you that had the path to where to download ParaView, and then there was that config file. So I sent them file to them.
Okay.
Right?
Okay.
So they should be able to do.
Yeah,
load servers instead of.
That's right. That's right. That's right.
Show them that.
So you can do. Let's try to do that. Okay. Let's see.
So when you say connect, right? So
the way I've done it is I used ParaView 5.4.1 and downloaded. Do this.
Right. So they should be able to go to connect. So
okay.
if you downloaded that file on your laptop somewhere, right?
You can do connect.
Connect, and now
and
say
then
load server
fetch, and load that.
Find that file.
Let's see if I have that. Oh, I have that. Okay. So let me delete that. Let me try that. So delete. So load servers, I have this file, yep, and that loaded all the files, yep. So the fetch part does not work, unfortunately, for this version. Another workaround is I use 5.4.1 version, and for that, fetch worked. I loaded the configuration file and then started this new version, and that had the configuration files already there. Yeah. So were you able to use the file to load the configuration files, the configurations? Okay. So I'm going to try to connect to Kuli. I tried twice until now, but it was always very busy, and my job was just sitting in the queue, so I was not able to do it. But let's try to do that now. Let's see. I have in the slides the values that you have to change. Yep. So if you are on a Mac, I think this is the right value. Can you see that? I'm going to make it bigger. So this is the right path if you are on a Mac. If you are on a Linux, you have to change that. I think the X term is in just user bin. Yeah. You have to put your username in there. Make sure the version is correct here. So in this case, it should be 552. That's an old slide. So that's 552. Let's see if we have the version correct in. Yes, and it's 80 PSC 2018. That's right. Yep. So the count and queue, is that the right? Are these the right ones?
It is, but currently there's only a handful of nodes that are reserved for this session. But it looks like there's a lot of free nodes, so you could probably just put default in the queue. Is that right, Marta? But that doesn't sound like.
So this is for Mac and for Unix. For Windows, you have to install PuTTY. For Mac, you have to install Xquartz. So, and these are the values for Windows. If you are on Windows, you can look there and make sure you change your username, account, and queue. So let's try to do that, at least to see what happens. So I should use default? Yes. OK. And the account is ATPESC 2018, yeah? So let's try to do that, at least to see what happens when I do that. And hopefully it's going to connect. So, OK. OK, so it says establishing connection. If I look over here, oh, I see the password, the login prompt. Try to connect that to generate my key. OK, enter. OK, so it connected. It says submitted these jobs to the queue. And then I think I have to press some value S to do queue stat. OK, so I'm in the queue there. Oh, it says starting. That's better than what I've seen before. I always seen queued, yeah. So let's wait a few minutes. OK, it says running, and it notice. So I have, yeah, this is exciting. I have the render view, and notice this looks different than when you run it on your local machine. So, you know, a simple thing we can do is do a sphere. Yep, so this runs on the HPC machine. How do I convince you of that? We can color by process ID. Yep, so we reserve 2 nodes. So basically, half of the sphere runs on one node, the other half runs on the other node. Yeah. So, yep.
Here that says display is not accessible on the server side. Like, is there something I have to change?
No, I haven't changed anything. We can look in the, tonight, I guess, in the session tonight, and try to yep.
So this is displaying which processor is reading which data on whatever you're running, I guess.
So what this shows you is that half of the sphere is rendered on one. So this is a sort of parallel-aware source, and half of the sphere is generated and is rendered on one of the nodes. The other half is rendered on the other one, and the sphere is put back together and sent to the client. Yeah. The sphere is, the source is written such that when it runs in parallel, it generates the individual piece on each node. If we had 4 nodes, you'd see 4 different colors. Yeah. All right, so that's, I don't have more than that. I have this memory inspector, so let's look at that. I think it's tools. Oh no, maybe it's view memory inspector. So here it shows you I have the client and I have 2 nodes, CC76 and CC31, and it shows you how much memory is on each of them. Yep. Okay, so I'm going to disconnect. Maybe that's going to help you guys get some access to the parallel machines as well. Okay. Oh, disconnect. Okay, so that's. All right, so Let's look at another case when that simple model we showed at the beginning, where you just do your processing as before on individual pieces of the data that are distributed to different nodes. Let's see a case where that doesn't work that well. So you have the same data, you distribute that on 3 nodes, and you want to find out the external faces, or in our case, external edges. Yep. So you compute the edges, the external edges for each of the pieces, and when you say that, hey, the length of the perimeter of my data set is, that is going to have some extra values, yeah? So you have basically twice the interior edges. So how do you fix this problem? This problem and many other problems are fixed with the so-called ghost cells. You might have heard of them before in your course, yeah? So what these are is basically you duplicate a row, one or several rows of cells at the interior part, at the intersection part, yep? So instead of having this blue data piece, you duplicate a row of cells there, and you mark those cells as being sort of special, called ghost cells. Yeah. And that's going to help also when you interpolate values that are close to the edge as well. So they help with many problems. So when you compute your external faces or external edges, in this case, you'll get the correct result because of that extra row of ghost cells. Yeah? So the internal edges don't contribute to the whole edge. Yeah? So and the result you are getting is the correct result. So with this simple trick, you fixed this algorithm and many others. When you partition your data, you have to sort of, your partitioning has to be load balanced. So that is, you have to hopefully have kind of the same amount of data on each node. And also it has to be spatially coherent. So the pieces have to be from the same place. If you don't, bad problems will happen. So in this example, we have data that's not spatially coherent, yeah? It's the same amount of data, you distribute that, but once you put ghost cells in, your data will be as big as sort of the original data. So that's the goal here. You want to be able to split your data and have smaller pieces of data on each node. If you have the same amount of data on each node, you don't gain anything. You run out of memory as if you run on a single machine. Yeah. So how do you distribute your data? Many times the data is distributed by the simulation and is written down on disk by the simulation. So it's already written in a distributed fashion. If you use a parallel reader, your data will be read individually on each node, so you can start running in parallel altogether from the reading step. Sometimes you don't have ghost cells generated by the simulation. We have a filter that helps you do that. It's called ghost level generator. So you can use this filter to create ghost cells for data that is already distributed, but it doesn't have the ghost cells. We also have a filter that distributes the data, but that's going to be time consuming. So if you have a data that's just on one node, you read that data and then you use this filter to distribute it on your parallel nodes. So in this example, we show what happens if you extract a surface without ghost cells. You don't get the correct result. If you add ghost cells, you get a much better looking result. So this is what I had for you guys. Check out ParaView tutorial. You have many more examples in there, and also ParaView guide. That's a very good reference. So thank you very much.